Alrighty, I think we'll get started. Welcome everybody to our theatre. My name is Jodie, and welcome to our Bubbleology show. Before we begin though, I just have a few housekeeping rules. I ask you guys all remain seated throughout the show. We do have some dangerous stuff up here, so I just need that distance between you and me to keep you guys safe. We also have two emergency exits. We have the one you came through and the one just over here. In the case of an emergency, I will tell you which one to go, but hopefully you will not come to that today. Our theatre, as well as the floor and our planetarium, are all food and drink free zones, so I just ask if you do have anything to keep it, yes, bubbles, to keep it in your bag. Alright, let's begin. So, we've all seen bubbles, right? Hands up, we've all seen a bubble before? Yeah? Awesome, I would hope so. So, can anyone kind of wager a guess what 4 things you need to make a bubble? Water? Yeah, water's one of them. Soap? Yes, soap's another one. Air? Yes, absolutely. And we need one more thing. That's the product, that's what we get out of the 4 things. What would the last one be though? We've got soap, what's this thing? No, this thing. So we call this a bubble wand. So we need a bubble wand, we need something to make the bubble with. So 4 things: water, soap, a gas, and a bubble wand. So I've got here my bubble wand, I've got some water in here, we're going to see if we can make a bubble. I need a countdown though from you guys. In 3, 2, 1.
Blast off.
Oh, hang on a second. No, nothing, absolutely no. So we've only got 2 things from our 4 things, and without all 4 things we will not be able to make a bubble, as you have seen. But I do have some pre-made bubble mix here, see if we can make a bubble. Bubbles. Pretty cool. Would you reckon I can go any bigger than that? Yes. Yeah? Go bigger than that. Come down. Come down. That's a good bubble. So good. You can go any bigger than that? Yeah? Oh, hang on a second. Do you guys want to see a bubble trick? I'm only learning this one though, so it might not work. But I see. Wait, what I'm going to do first. Little trick that you guys can do at home. If you are blowing any bubbles, it works a lot better if there is moisture in the air. So I'll see if I can prove myself right here. Oh, hang on. There we go. Bigger than that? Yeah! Yeah? Alrighty. Let's do it again. We'll go one more time. There we go. Nice. Do you reckon I go even bigger than that? Yeah. I don't know. I wish. Alrighty. So can anyone notice what shape that bubble was? So kind of, it's like a 3D circle. That's exactly right, it was a sphere. But I have a star-shaped bubble ones here. Do you reckon I can make a star-shaped bubble? Yeah? Alright, I'll see if I can make a star-shaped bubble. Oh, hang on a second. Hang on a second. What is happening? Alright, so unfortunately it doesn't matter what shaped bubble we have, shaped bubble one we have, we will always make a sphere-shaped bubble. That's because bubbles are very, very lazy, so they like to be the best smallest shape they can possibly be, which is a sphere. It's unfortunate, I would like to see a star-shaped bubble today, but we are not going to be able to. There we go. There we go. So can anyone tell me if this is a open or a closed shape? What do you reckon? It's a circle, yes, but is it an open or a closed shape? Closed? Yes, absolutely, it's a closed shape. Yes, it is a circle. So, yeah, it doesn't matter that there's a hole in the middle there, it is a closed shape. This is very important for our bubble wands, because if it's not a closed shape, it will not work as a bubble wand. But that also means that we can use pretty much anything as a bubble wand, as long as it has a bunch of closed shapes, like this guy. This guy has a lot of closed shapes on it, which means that when I dunk it in my bubble mix here, I can do this. Again? Alrighty. Let's do it again. We ready? It's shouting bubble mix here. Again? We'll do it one more time. I'll tell you what, we sell these in the gift shop, so if you want to do it at home.
Can we teach us how to make it?
How to make bubbles? Make this or make bubbles? Which one? Make bubbles? Soap and water. That's it. See the detergent? I've got here dishwashing liquid. You're just getting soap and water. You need something to, you need a bubble wand. Blow into it, bubbles.
Can we make it? Can we see how we make it?
Yeah, well, I'm doing that later in the show actually. I've got a pre-made some bubble mix over here. So I'll show you later on. But, does anyone play badminton or tennis? Yeah? Has anyone just got like a racket at home that they're no longer using because they thought they'd play tennis? I got a use for it now. We can turn that racket into a bubble wand. I don't know what you're saying, but I love it. Yeah, we also have this guy. So you can't really see it, but on this is a lot of very, very tiny little closed shapes. Because they're so tiny, you can make very little bubbles that look something like this. Losing my breath here. And now we have a bunch of bubbles. I should have gone there, that's wet. That was a bit bad. Not the moment. Alright, so what were the 4 things again that we needed to make a bubble? You're so confident there. Water and soap, what was the other ones? Gas, yeah? Yes, and a bubble wand. So, what you guys were seeing there was bubbles made out of just the air that we breathe. That's the usual bubbles that we make. However, you can make bubbles out of any gas. So what I've got here is liquid nitrogen. Has anyone seen liquid nitrogen before? Yeah? Caesar, I'll show you what it looks like. a bubble out of our liquid nitrogen. So pour my thing into here. Yeah, absolutely. I'm actually really excited because it hasn't worked for me in the past 4 shows. This is great. I broke my string. Yes. That's pretty cool. I'm so excited about that. I've been disappointing so many audiences. That's amazing. Alright. Let's go back to there now. Pretty cool. What you guys are seeing there isn't actually liquid nitrogen. So the liquid nitrogen has actually already evaporated before it even hits the ground. What you're seeing there is frozen water vapor that was in the air that is now being condensed into fog. Pretty cool. We've got a little cloud on the ground now. Alrighty. So I'm going to make a bubble mix now. So I've got a bowl of water here. It's literally just water. I've got my dishwashing soap. Don't know if you guys use the cold spray. Chuck a bit of that guy in. Change something to mix it around with. Doesn't have to be this. And then we get. So we're using a different gas this time. This time we are using a flammable gas.
Can we see?
Yeah, of course. I'm going to show you. First of all, though, we're going to put this guy on. So I've got my water, I've got my stove, I've got my gas. Can anyone wager guess what my wand is going to be?
I don't know.
Exactly right. I'm going to use my hand as a bubble wand.
Ew!
Are you ready? Come on. Ah! Alright, ready? No. There you go. Get a bunch of those out. Spray this on. Alright, are you ready? 3, 2, 1. Thank you. So I do it one more time?
Yes.
Yeah? It's probably keep this on, but I took it off now, so. Again? I'm doing it again. I'll do it one more time. Just gotta spray this one on me first. So I don't know if I have to. This is pretty obvious, but no one try this at home. But I do need you guys to promise me that you will not try this at home. Thank you. Are you ready? 3, 2, 1. Sorry, anticlimactic. I'm not doing it again. That scared me. Oh my god. That's fine. I'm good. I'm fine. It's okay. I'm good. Downside of being half Maltese is I have a lot of hair that goes up. No. Absolutely not. No, I'm all good. I have like a little bit of bubble mix on my hand, other hand. It's fine though, it's fine. Don't even worry. Don't even worry about it. Cool. So that's all the experiments I have for you guys today, unfortunately. But I took a little bit of time for questions, if you guys have any questions. That is good to know. Anyway, okay, cool. Thank you. In a moment, I'll go over the doors for you, and I hope you all enjoy the rest of your time here at Science Days. Thank you. Thank you.
Alrighty guys, welcome to Science-Based Science Theatre. My name's Joel, I'll be doing the show today. So before we get started, I was going to run through a couple of safety things. We've got two emergency exits, one to my right, one to your left, and then also one to my left and one to your right. There's only two exits, it's not four, don't get confused, I get confused all the time. Anyways, so they're the two emergency exits. I also ask that you guys don't run up and jump up out of your seats at any point unless you've been called upon down to the front, just for safety reasons, in case I'm dealing with LM. I don't really want to freeze dry you, that doesn't sound great. And also, if I do have to let any of you out because you need to go to the toilet or anything, I can't let you back in, so that's just your sort of first and final warning for that. But it's only a 20-minute show, so hopefully you can hold it in, or whatever it is, hopefully you can wait. So, moving forward, this is our LM show. Who knows anything about liquid nitrogen? One person. Awesome. You guys are in for an education, that's for sure. So, what do you know about LM? What do you know about liquid nitrogen?
I know it starts with L and the end with T.
The liquid does, that's correct. You're not wrong. I can't fault you for that. You do know something about liquid nitrogen. So, who thinks it's a hot or a cold liquid? Does anyone know what they think it might be? It's a cold liquid. Yeah, how cold do you guys think it might be? What did you say?
I think it's negative 30 degrees.
Negative 30 degrees? Well, I'll pour a little bit out, and I want you guys to tell me something about it. Yeah, right, let's put my gloves on. Good catch. That could have been very cold and very nasty. I wouldn't get hurt, but it just wouldn't be nice. So, has anyone boiled water before?
Yes.
That's good. You guys cook. So, that's boiling, isn't it? Do you guys think that's boiling?
Freezing cold.
Freezing cold, but it's bubbling like boiling water. Well, that makes sense. So, yeah, what's actually happening here is liquid nitrogen is actually negative 198 degrees Celsius. So it's quite cold, something that you really don't want to spend too much time with. So, negative 196, my bad guys, I got the number wrong, as per usual. So, but it's still boiling. That's because it turns to a liquid at negative 196 degrees Celsius. But as soon as it comes above that temperature, it starts to boil. It starts to turn into a gas. Similar to how water boils at 100 degrees Celsius, this stuff boils at negative 196 degrees Celsius. So that's pretty cool. I'm just going to pour some out and you can watch that. So it's a very cold liquid and it boils at a very low temperature. So, just for reference, that's the absolute lowest temperature we can possibly get ever. That's with zero amount of energy whatsoever. And on Earth, that's the coldest temperature we ever experience. So there's quite a stark difference between how cold it can possibly get on Earth and how cold this stuff really is. So does anyone think things change when they get cold? Do the properties of things change when they get cold? What do you guys think? They do, don't they? Like water turns to ice. That's the best example I've got. I've also got some rubber here. Do you think rubber's properties will change when they get cold? Got a little bit of rubber. So it's quite flexible right now. Band's really good. Rubber, nothing special at the moment. What do you guys think is going to happen when I allow this rubber to get nice and cold inside my car? What do you guys think is going to happen to it? Yep.
I think a show, I saw something, they put a table tennis ball into liquid nitrogen, and when it took out, it was like really bouncy.
Really bouncy. I've actually got a similar thing later on as well. So I've got two bouncy balls here. As you can see, they're just plain old bouncy balls. Nothing too special going on here. No witchcraft yet. So I'll put these back over here for now. But while that's happening, we'll lose that one. I'll put it back. So I'm just trying to get my cup nice and cold, get my rubber tube very cold. Can anyone hear that? It kind of sounds like a little bit different now, doesn't it? Sounds kind of stiff. Now what do you guys think is going to happen if I hit this with a hammer now? You guys think it's going to just sort of still be rubber? Think it's going to change properties? I'll clear out this table so nothing falls off when I hit this little hammer. So, well, let's find out. I'm going to put this on my little kit here. Ready? 3, 2, 1. It shatters. So that wouldn't have happened to our original rubber tube. Here's our original one. If I hit this now, so the properties of our rubber have completely changed. They've gone from a really flexible solid to a really stiff and brittle solid. And because this is rubber, even though this is now about negative 196 degrees Celsius, I can actually pick this up because rubber's a really, really good insulator. So I can sit that around, play with it in my hand, and it's not really that big of a deal. So, what do you guys think is going to happen to my rubber ball? Any ideas?
Bounce very good.
It's going to bounce? If you guys think it's going to bounce better?
It's going to bounce better.
Well, the rubber ball sort of like bends a little. It's kind of squishy, isn't it? And we saw that's because it's rubber. And if my other rubber got frozen solid, what do you think's going to happen to my ball? Do you think it's going to get frozen solid and be less squishy? Do you think I'll make a better bouncy ball or a worse bouncy ball? A worse one? Some are undecided. Well, let's find out. Ready? I'm going to drop my bouncy ball from about the same height. Kind of bounces a lot worse. And you heard it, sounds like a rock now. It's just very solid. And once again, even though this is super duper cold, I can pick it up and play with it because it's a good, really good insulator. I can let one of the people in the front audience feel that. Make sure you juggle it, don't hold it in one hand for too long. It's cold to the touch, isn't it? Pass it around a little bit, it'll probably warm up by the time it comes back. So, that's what we know about that. So we know things change properties when they get cold, but why is that? It's because we're taking energy away from things. Now what do you guys think is going to happen to this ball and a hoop when I pull the hoop down specifically? I'll show you right now. At the moment, the hoop can pass straight through. The ball can pass straight through the hoop, and there's not much of an issue there. So that's pretty cool. We can do that all day, all long, no worries. But what do you guys think is going to happen when I pull down the hoop? It can't go through, do you think? So do you think the hoop's got smaller?
Yeah, because like it's got, yeah.
So I think the hoop's going to get smaller when it gets cold. Let's find out. I'll let that simmer in there for a moment. It's a bit like a cooking channel, except for changing the matter of things, because why not? Get it nice and cold. Our ball now went past through our hoop. So our hoop has actually gotten so cold, it's actually contracted. So when things get cold, they like to get smaller, exception of water. When it turns to ice, it turns into a cube, so it gets bigger. It's kind of interesting. Kind of a weird phenomenon. But when things get cold, they like to be, all the molecules like to be squished together. They try and warm each other up, and they're like, oh, let's stand closer together, it'll be nice and cool, nice and warm. Oh, that's great, that's warm. When they get too hot, they're like, all right, get away from me, you're too hot, I'm sweating, this is horrible, I don't want to be here anymore. So they try and expand out. So that's essentially what's happening with our molecules. And what we did with our rubber tube over here is all the molecules got really close together, That's why it lost its elasticity. They got too stiff, they were too close together, and we came over with a hammer and we broke them all apart, which wasn't very nice of us, but we did it anyways. So, if we know that solid matter contracts when it gets cold, do you guys think of air in a balloon will contract when it gets cold? Any ideas? Yes, no, maybes?
Yes.
Yes? I'll pour a little bit on there for now. I'll get my big container out. You guys hear how the balloon sounds now? It sounds a little bit different, doesn't it? It doesn't really sound like a balloon anymore. It sounds like a trash bag. So yeah, our balloon has shrunken. Do you think I've like lost all the air?
Yes.
Well, I can actually blow this up from the outside now. How could I do that? That's a great question. Who thinks they might know what's happening here? Anyone know what's happening here? Alright, good. You guys are going to learn something. So, what's actually happening there is we're cooling down the air. The air is doing the same thing as what solid matter does. It compresses. It gets nice and close to each other and they cool down. That's how they try and warm up. It's the best way to think about it. So what I'm doing is I'm letting it get nice and cold inside of my little LN bath I've got going on here. And when I take it out, the warmth of my breath is enough to warm up all the air particles inside of the balloon and make it expand again. And we can also hear that the balloon's properties are kind of changing as well, just from the sound of that plastic bag kind of sound. So yeah, let it get nice and cold again. So we've got ice in there somehow. A little bit of ice from the outside of the atmosphere. But if we're lucky, we might also see some interesting things on the bottom here. So what I've got dripping off there is a little bit of condensation and also a little bit of liquid oxygen. Liquid oxygen freezes about around 80 degrees Celsius. So what's actually happening there is we've got some liquid oxygen bouncing off, hitting the ground, instantly turning into a vapour. You can tell it's liquid oxygen because it's not just staying as a liquid. It's going straight back to a gas as soon as it hits the ground. And if we're lucky, we might also get some solid carbon dioxide, which is what that little bit of frost around the outside is at the moment. That's solid carbon dioxide. I'm not going to touch this because it's really cold and there's a good chance my finger will get stuck to it and that's going to be really awkward for the show. Because doing a show with a lock attached to my hand doesn't sound fantastic. So I'll sit that back down there. And would anyone from the front row like to have a go at blowing up the balloon from the outside? Do you want to stay seated? I'll bring it over to you. Give it a blow.
Don't touch it.
Don't touch it, just blow.
Just blow. Gonna give it a go?
Very cool.
Thank you.
Pretty much fully inflated. Oh, have a go if you guys want. Go nuts. I'll only throw it back in the bath and make it smaller for you. Rightio, so we've pretty much got our balloon back to its original size, more or less. So throw that back in the block and let it reverse cook, not cook, but uncook, I guess. Not really sure what the technical term for that is. So if we know that things expand and contract when they get hot and cold, do you think LN itself can do that? Liquid nitrogen? Do you think it expands when it gets hot, guys?
Yes.
Yes? Would you call room temperature hot? No, I wouldn't call it either. But to liquid nitrogen, it likes to exist at negative 196 degrees Celsius. So room temperatures to liquid nitrogen is about like as if it's 200 degrees Celsius to liquid nitrogen. It is very cool, I agree. So, what I'm going to do here, so before I start this experiment, I'm going to preface this. When I do this experiment, it's going to be a very loud bang. So when I put my headphones on, which will be the green ones, I want everyone to cover their ears as well. Not right now, don't stress. It always happens. But for any parents that are concerned about their toddlers, I do have some headphones to put on the toddlers. Yeah, bring them up to you.
Okay. Do you want to do
One over there as well. No worries. Another young one over here. Try and give it to the youngest members of the audiences.
Yeah, honey. Just use your hands, yeah?
So what I'm going to do is I'm going to put LN into this bottle and I'm going to put a balloon on the lid of the bottle. And then what I'm going to do is I'm going to dip that really cold liquid straight into this container full of room temperature water. The stark difference in temperature is going to make the liquid nitrogen expand really rapidly, and you'll see me sort of panic and put the headphones on very quickly. And that means it's time to cover your ears because this bang is very loud. I did it without headphones the other day. It really hurt my eardrums. They rang for about 15 seconds, and I don't recommend it. Don't try and test Faye, it's not good. So I'm going to begin now. So when I put my headphones on, that's time for you to put your hands on your headphones. A little bit more. I don't want to do too much because it'll expand very rapidly. So I'm going to recommend everyone cover their ears now. Everyone's covered. Alrighty, I'm in smoke, believe it or not. So yeah, being this long out your ears covered, quite deadly. You're going nuts for all of that over here. I can just sit there for a minute, that'll be fine. I think this might be long. So, that's a pretty cool experiment as well. Now, I have one more thing today. Once again, demonstrating how liquid nitrogen expands when it gets hot, or cold, I should say. So what I've got here, so I'm going to fill up a little bit of a container with some hot water. Now, we call this one the fog bomb. Does anyone have any idea why I might call it the fog bomb? A few people. Well, save your ideas, and when I do it, I want you to think if that's exactly what you thought was going to happen, because the name might be in the details. Alright, ready? 3, 2, 1. Exactly what you thought? Yeah. The name's a bit of a giveaway, isn't it? So, does anyone have any questions about our land today? Any questions? Yeah, one in the middle. Just one of the tension, that's alright. Yep. A touch of the balloon, which one? This one? Yeah, of course. Well, I might be out of LN. Well, no, I am out of LN. It's just a regular balloon now. I don't know if you still want to touch it, but you can for sure touch it. There you go, it's a balloon. Very good insulator as well, so it really won't feel the cold after this. You feel water, yeah, because the water's condensing on it from the atmosphere. It's always condensing onto our balloon, because we got it really cold. But I will also show, because it always happens better on the bottle than it does the wok, but we got a little bit of dry ice, aka solid carbon dioxide. You can tell it's that because it doesn't have a liquid phase. It skips liquid and goes straight into a gas again. So I can't even really get damp from this stuff. So that pretty much brings us to the end of our show today. So you guys have any last questions? Yep, one in the middle. Where do you buy liquid nitrogen? That's a mystery to me as well. They sort of just give me a big vat of it and they go, that's you for the day. I'm like, okay, I won't question that. Any other questions? Yep. How does the balloon pop from the liquid nitrogen? It's because liquid nitrogen is actually a really cold substance. And as we demonstrated, when things get hot, they expand. And we're going from negative 196 degrees Celsius all the way up to positive 200 degrees Celsius. So we're changing temperature about 200 degrees roughly, give or take. So that rapid expansion causes everything in that liquid nitrogen to expand. And it's also worth mentioning, nitrogen is actually in our atmosphere. It's 70% of our atmosphere roughly. Changes a little bit. And so it's not really a harmful substance. That's why we can sort of just let it go nuts over there and go into our room and pull everything down and try to. It's actually our air conditioning. That's a lie. It doesn't work that good. So also, one more interesting thing. Look how our balloons pop. It's kind of a funny way to pop a balloon. Anyone popped a balloon before? Yeah. It doesn't pop like this, does it? Yeah, that's because, once again, we've cooled something down. We've changed the properties of that balloon. So when it explodes, it actually gets really cold and it loses elasticity once again. So when it pops, it doesn't really pop all at once. It pops several different places all at once, and that's why it shreds like that. Does anyone like to take this blown balloon as a souvenir? I'll give it further up to the back row. I'll go blue shirt. No, I won't go red shirt. So that brings us to the end of our show. You guys have been a great audience. My name's been Joel. I'd like to thank you all for coming today. I'll open up the doors and I'll let everyone out.
Oh.
100,000 of them. Look there. How did they come out?
They come from outside. This is honey. That's honey.
They come out from outside and so the ones at the top are going outside the ones. Look, they're walking. It's so cool. Is there a button? Look, you can even see them.
The whole elephant's moving, the trunk and all. As if you're spinning it.
I can make.
Show me.
Alrighty. So without further ado, we'll let everyone get seated and we will start the show. So first off, my name's Joel. Nice to meet you. Welcome to Science Based Science Theatre. So this is the fire show. I'll let you know now, we don't do volunteers for the fire show because having random strangers handle fire, especially children, just doesn't sound like a good idea on paper or reality, so we don't do that. In the event of emergency, on your left will be an emergency exit here, and also one on your right. It'll be up to me to remember that you guys have the opposite lefts and rights, and I will be directing you to the right one, hopefully. We also have a fire extinguisher and a fire blanket up the front in case anything goes wrong. In the event of a good emergency, I'll be the one to use them. In the event of a very great emergency, hopefully someone will have the initiative to use them. So, without further ado, let's get into the fire. Oh, sorry, one more thing. If you have to leave the show through any point, I can't let you back in. That's the only thing I have to preface. So, without further ado, I'm going to turn the lights off and I'm going to talk about fire. So, what I've got here is a fire. Awesome. So, what do you think is going to happen to this candle when I put the lid on this jar? Yep. It's going to lose oxygen and it's going to go. That is the correct answer, and that is soaked up 2 minutes of my time. Perfect. Awesome. So yeah, that's what's going to happen. The fire's going to sit there, it's going to lose its oxygen, and it's going to die. Does anyone know what fire generates? I'll get someone different. You're very smart. It generates heat. You're correct. Fire does generate heat. I'll get someone else. You're really good at answering questions. You're going to ruin my show. Anyone else got any ideas? What else does it generate? Yep. Carbon dioxide. Exactly right. So it generates heat and carbon dioxide. So what do we know that a fire uses? We know that fire uses oxygen. Does anyone know? So if we try and breathe on it, should it get bigger or smaller? Up the back, yep. It should get bigger if we blow on it. In the right conditions, yes, but what do we breathe out? Air, but what kind of air? What gas exactly? Go up the very back row. We breathe out carbon dioxide. We're not fires, but we breathe out the same thing, and we breathe in the same thing. So when we try and breathe onto a fire, we're actually just breathing out more carbon dioxide. So yes, you can add more oxygen to a fire and make the fire bigger, but carbon dioxide is just no good for a fire. That's why it's really tricky to blow on it. And that's why our fire has now gone out. So I have another demonstration now. I have some mysterious powder. Does anyone know what this powder is? Any guesses? Let's go you, yep. What was it? It is not gunpowder. Let's go in the middle, yep. Baking powder? Plain flour, not plain flour, no. Up the back left. Your back right. Yep. What was it? You forgot? It's alright, I almost forgot at one point. No, so the correct answer is bicarb soda. Does anyone know what would happen if I added vinegar to bicarb soda? What do you think we're going to generate? Let's go blue shirt.
It's going to explode.
It's going to explode. Well, I hope not, because I'm the one doing it. And if it exploded, that's not going to be really great for my health or well-being, I don't think. But you guys aren't here for that. So I'm going to mix it now. Pour in a little bit. And what do you guys notice that we're generating? I hope you guys can see in the dark, but what's that generating? Is that generating something? Yep. It's going to generate air, but what kind of air? Like what do you guys think? Any ideas? Up the back left?
Carbon dioxide.
Carbon dioxide, exactly right. We're back to our common theme, by the way. Here we are. So we know that carbon dioxide is no good for setting fires. So do you guys think I could use what I've generated in here as a fire extinguisher? Just shout it out, yes or no?
Yeah.
You think I can? Let's find out. I'll get them all lit without the candle going out. Awesome. So yeah, I think I could probably use this as a fire extinguisher. I have a bunch of carbon dioxide gas. Fire doesn't like carbon dioxide. So hopefully, if I pour it out right, I can extinguish the flames without even touching them. So that's the premise of how our CO2 fire extinguishers work, which is very cool. I won't turn the lights back on now because they don't need to be off anymore, at least for now. So that's very cool. That's how a fire extinguisher works. It's just a bunch of CO2, and that's why when you go to put out a fire, you should aim towards the base of the fire, because that's where the rest of the fuel's burning. That's where we need to turn everything off. So if we flood that area with carbon dioxide, no oxygen, we can't breathe, the fire just passes out. So we've talked a little bit about it. Who can name the 3 things that we need for a fire? We'll do one each. One thing.
Oxygen.
Oxygen, correct. Next thing.
Carbon dioxide.
We don't need carbon dioxide for a fire, that's what it creates. Yep. Yep.
You need fire.
You need fire? Oh, I'll almost give it to you, I'm not going to. Any other ideas what we need for a fire? Yep.
Fuel.
Fuel, exactly right. That's 2 things. One more thing that we need. Let's go somewhere different up the back row. Yep. A lighter? What is the lighter adding to the fire? Is the lighter cold or is it? It's hot. We need heat. That's right. So they're the 3 things that we need for a fire. I'll just skip past the slide. Let's go. Right, one more time. There we go. Fire triangle. Here it is. So we take any of these 3 things away from our fire, and our fire triangle collapses. Has nothing to stand on anymore. It's no longer the strongest shape. So what we've done here is both times we've taken away the oxygen supply. That's what we've taken away from our fires. So what else could I take away from my fire? Any ideas? Yep. Take away heat. It's very tricky to take away heat from a fire because it generates heat. So in theory, yes, you can do it, but it's very, very tricky to do. Yep. Take away the fuel. That's a great idea. Let's try and do that. So what I'm going to do now is I'm going to create some flammable gas bubbles. This is flammable gas number 1. I can't tell you what it is for legal reasons. So I've created a bunch of flammable gas bubbles just now. Now I'm going to coat my hand in water. Some of you are now thinking, what is this guy doing? Has he lost his mind? A little bit. Anyway, so how do you guys think this is going to work? Do you think I'm going to catch on fire? Yeah? Do you guys want me to catch on fire?
No,
You guys are
no.
bullies, I don't like you. Well, let's just see what happens. So I've got some flammable gas bubbles. Got a line that just barely works. That's very what it is. That one. All right, let's get a big countdown from 5, 4, 3, 2, 1. So, would anyone like to see that one more time while I explain what's going on? You still want to see it one more time or 2 more times? 2 more times, of course you do. The show's not fun unless Joel's on fire. Very good. So what I'm trying to do here is I'm trying to take away the fuel source. Now, if I let the fire sort of stay in my hand, I probably would become the fuel source. And that's not something I really want to do today. I don't really want to be burned up into a fiery ball. So what I do is I remove my hand from the situation, and the flammable gas is all that's left in the air, and it just burns away. Ready? 3, 2, 1. That was a good one. That was a scary one. My eyes just watched. So, you guys did say you want to see it 2 more times, so 1 more time, let's go. What was that? Yeah, I did think about it. I was like, trying to remember where they were. I was looking on the tables for them, like, where are they? Did that classic thing.
I've got a question.
You got a question?
Can you like this type bowling fire?
I'm not going to do that, it's very scary.
What?
Alright, these bubbles kind of sketching me out, but we're going to run with it anyways. Alright, ready? 3, 2, 1. Very cool. So what we're doing is we're burning up all the gas. That's all the fuel. It's burning up in the air. It's off of me by the time it burns. So I don't get burned. And that's a good thing. That's a good thing, everybody. Me not getting burnt is good, contrary to popular opinion. So we've taken things away from fire. What can we add to a fire? What's the easiest thing that we can add to a fire? Any ideas? Let's go. You guys haven't had one.
Like wood.
We can add wood to a fire. We could add wood to a fire. We could do that. We're not going to, but we could. Up the back left, back right. Make it bigger. I want a bigger fire.
More heat.
We could add more heat. It's kind of tricky to add heat to a fire as well because fire is already really hot. So any heat that I add to it's not really going to do a whole lot. Well, I've got a little demonstration here. I've got flammable liquid number 1. I can't tell you what it is for legal reasons. So once again, flammable liquid number 1 is going into what we call a ramekin. I don't know where a ramekin comes from, but that's the name it has. So what I'm going to do is I'm going to set this on fire. I'm going to put this over here and put this over here so I don't have a big fireball blow up and destroy me completely. Like that. Now that's lit. So we have a bit of a fire going on. Very cool. That's a great thing. We're in the fire show. That's what we want. So where this fire sits right now, if I spin it, nothing's really happening. The fire fluctuates a little bit, but nothing really happens. Now, how do you guys think I might add more oxygen to this? So we're looking for hands. It's in the dark. Yep, over here. We added fuel. Well, we've already got our fuel. It's burning away there. Any more than I add is not really going to change the rate that it burns. Yep.
Oxygen?
We can add oxygen. And how might I do that, do you guys think? We're going to blow on it? It doesn't really work. We sort of established that before. I'm breathing carbon dioxide. The fire doesn't really need that. But what if I put a random trash can on top of it? All of you are like, why have you put a trash can onto a fire? And that's a fantastic question. So as you can see, our trash can's full of perforated little holes. Now, as you saw before, I spun the table. The table can spin. That's a really cool thing it can do. Little lazy Susan, as they used to be called. I don't know if they're still called that or not. But what do you guys think is going to happen when I spin it now that I have the trash can on it? Any ideas? Yep, in the middle. It's going to get bigger. Well, let's see what happens. There's a little bit of a fire tornado. Maybe that a bit more centered. It doesn't fall over and cause a catastrophe. That's a really good one today. So, does anyone think they know what's actually happening here? Why does putting the trash can with a bunch of holes on top of the fire make a fire tornado? Let's go up the back left, back right, your back right, mine left.
The fire is getting more oxygen because the holes are spinning around so
pretty good answer, honestly. So you're more or less pretty much right. It's the holes are causing the oxygen in the air to be drawn in from the bottom and they're being expelled out through the top. We're making a convection current is what's happening. So the hot air up here is spinning around, it's sort of going off into the atmosphere, that's hot on my eyes. And the cold air is being drawn in from the bottom because all the hot air is going up and away. So that's very interesting, don't you guys think? Now, how do you guys think I might put this fire out? Any ideas? Let's go just here.
The ginormous bottle over there, the ginormous jug over there, you can fill it with water and spread it on the fire.
Put a jug of water on it? I probably shouldn't because this is a chemical fire. If I put a bunch of water onto my chemical fire, all that's going to do is make that chemical fire just stand a little bit higher in the bowl. Worst case scenario, it spreads everywhere and I get a big fire. And my boss is like, Joel, what happened? And I'll have to be like, I put water on a fire, chemical fire. But the easiest thing to take away, thinking back to our fire triangle, is oxygen. So if I just take this little plunge, our fire's extinguished. Just that easy. So that's how we can extinguish a fire that's sort of burned away like that. So in the event of a chemical fire, you shouldn't put water on. It's going to be the worst thing you could probably do for that fire. So moving on, what's the time then? Oh, I've still got heaps of time. So I've got what I call, does anyone know what this might be called? You've probably seen it in your life. Anyone got any good ideas? Yeah.
A big water bottle.
A big water bottle. That's correct, it's a big bottle of water. So, does anyone know what else they could possibly do in the event of a fire show? Yeah.
Burn it.
We could burn it. We'll burn it to the ground. We'll melt the whole thing. No, we're not going to do that. So, what we call this here, we call this a whoosh bottle. Does anyone know what I call it? A whoosh bottle. Because it goes whoosh. It's a good question. It's a good idea. Kind of silly though. That's kind of a silly answer. I don't think that'd be right. Anyone have any other ideas why we might call it a whoosh bottle? Yep. Because it's going to go whoosh? I don't know. That'd be kind of too easy of an answer, don't you think? Anyone else? Any other ideas? Yep. You're basically right. I can't fool you guys, it seems. I can try and tell you got the wrong answer, but you don't. You're absolutely right. It makes a big whoosh sound. That's what we call it, the whoosh bottle. So what I've got here is flammable liquid number 2. Once again, can't tell you what it is, legal reasons. So flammable liquid number 2 is actually very, very flammable. And I don't even want to light the liquid of this. I just want to light the vapors. So what I'm doing right now is I'm coating the inside of this with a bunch of flammable liquid number 2 vapors, or flammable vapors number 2. So if I now pour these back into this, because I don't want the liquid in here. The liquid is just going to burn too good. It'll probably detonate my bottle, which would be very scary for me and concerning for you. So I'm going to move all my flammable liquids off of here. I'm going to turn the lights down low now. I'm going to go back across the room to go get the one light that works apparently. And what I'm going to do is I'm going to put on one glove, just one, that's all I need. There we go. Alright, we'll get a big countdown from 5, 4, 3, 2, 1. Incredible, awesome. Alright, we'll do it again. 3, 2, 1. Hello. So who thought that was pretty cool? No one. Awesome. It smells, doesn't it? You can smell it. So, would anyone like to see that one more time with this bottle? You want to see it with this bottle? Well, before I show you what can happen, before I do it again with this bottle, this is my friend Alfred. Alfred's not good for much, he means well, but unfortunately this is what happens when we do it twice with one bottle. So it deforms the bottle, and because it sort of comes out a bit like a projectile, that's not fantastic, because it might sort of do this and then go everywhere. So unfortunately I can't do it with the same bottle, guys. Luckily, we've got another bottle. This one's not named Alfred. This one doesn't have a name yet. We only give things names when they break. So, who would like to see that one more time with a different bottle? No one? Yeah, we do. Okay, awesome. I was looking for the energy, guys. Playing with fire, let's have fun. So, So once again, I do have to do the whole shaking thing. So did anyone notice how that fire burned? It didn't burn all at once, did it? It sort of burnt from the top down to the bottom. Do you guys think that's what happened? Yeah. So it's actually kind of interesting. Because we have like a nozzle shape, it's kind of like a rocket, we actually control the amount of oxygen that's coming in at a time. So we burn from the top down to the bottom because the oxygen's rushing in from the top, all the heat's getting expelled and launching out into the atmosphere. So it's very cool that that happens. And that's kind of the premise of how rockets work. Because if rockets burn everything at once, they wouldn't get very far. They'd sort of probably just blow up on the station, which wouldn't be fantastic.
Can you burn with the liquid in?
I've already put the liquid in.
With the liquid in, you're not pouring it out.
I'm going to pour it out. If I don't pour it out, it might detonate, and that's concerning for me, worrying for you, and my boss will be like, what's the go? And I don't really want to tell him what's going on.
Who is your boss?
Who is my boss? He's a very stern gentleman, which no, he's very fun. So, ready? I'm going to turn the lights off one more time. I have the common theme. Alrighty, get a big countdown from 5, 4, 3, 2, 1. There you go, guys. That's our second wish bottle for today. So, you guys may have noticed, after I burnt that wish bottle, I put my hand on top of it. Did anyone notice that I was doing that? Who thinks they might know why I'm doing that? Yep.
Carbon dioxide from going, so then the fire will just go out.
Yeah, pretty much. So what I'm trying to do is I'm trying to limit the oxygen going back into there, because the fire can still be ignited, but I just can't see it with my eyes. And your eyes might be better than mine, but hopefully you can't see it either, and that way it makes more sense. But by doing that, I'm making sure that I have restricted all the oxygen going into the fire, it's burnt up all the fuel and the oxygen that's inside of the bottle, and it just goes out, so I don't have a big issue. Which is also why I've left the tapper on top of the other ramekin. That's because the ramekin got quite hot. It gets very hot very quickly. And I don't want it to self-ignite while I'm over here doing the rouge bottle, which is why I just leave it on there, let it cool down, wait for the heat to disappear out of our fire, because we don't want it to self-ignite. It's one of the 3 things we need for a fire. So by restricting one, we take away the power of the fire. Does anyone have any closing questions? Because that brings us towards the end of our show. Any questions? Right at the back. How does fires occur in bushfires? Well, that's a really good question. So most of our fires happen in summer, don't they? Whereas there's more heat. There's more heat now, land, there's more heat in the country, so it's very easy to set a fire by accident. That's usually what happens. If something got left somewhere like a can or a lid or a bit of glass, that self-ignites the grass that's underneath it, and our fire gets carried away. But in winter, it's a lot colder, so it's a lot harder to start a fire in winter because you need heat for a fire to begin with. So that's kind of why we get more bushfires in summer. So that's a good question, thank you. Any other questions? Yep.
Why does the fire, when you do that, change a bit from orange to blue?
This is more to do with like the rate that it's burning. Sometimes they burn a little bit faster and they release more energy. The more energy it releases and the less energy it releases changes the colour of the fire. So more about rates of fire and what exactly it's burning. Yep. What if I pour liquid nitrogen on the fire? Liquid nitrogen itself would probably expand very quickly, and I don't think it brings in a whole thing of heat capacity, and I don't think liquid nitrogen has enough heat capacity to put out a fire. With enough heat, with enough liquid nitrogen, you probably could. But also, liquid nitrogen doesn't burn, so it probably just do the same thing as carbon dioxide does. So that was a good question, thank you for that. Yep. What's my favourite science experiment? It's a good question. Unfortunately, I really like boring stuff that's in the lab, so it probably wouldn't be very interesting to you, but I like watching stuff change colour. That's very cool that I like to do, which is nothing I do here, unfortunately. Any other questions? Oh, that brings us to the end then. Sorry, oh, one more.
How does fire get bigger if you just let oxygen go into it? Because if there's too much oxygen, won't it make the heat go away?
That's a good question. It's definitely a balancing act. So more oxygen will mean there's more things for it to burn. So it burns a little bit faster because there's more oxygen, there's more chance interactions happening. But the wind itself, the temperature of the wind doesn't really affect it too much. You'll probably find if you're in somewhere extremely cold like Arctica or somewhere like that, it wouldn't matter. It'd be too cold to sort of start a fire. But because the wind's bringing more oxygen, it's bringing in more heat as well. Once the fire burns that oxygen, it creates more heat, keeps itself ignited, burns more oxygen, keeps going. That's sort of what happens. It's just a constant feedback loop. Alright, I'm going to call that there. You guys have been great. Thank you for coming today. My name's been Joel. I hope you've enjoyed our shows today. I'm going to open up the doors and let you guys out.
Knock, knock. Welcome, Luna Park.